Okay. Of course, linear models have assumptions which are different from the ones we saw before. First assumption is linearity. You check. Okay, we still have half an hour left. First assumption is that you would expect so it should be a linear equation. First of all, linear equation is simply about the form of the equation. So you should have, it should be kind of additive like we did. So if we look at the previous slide, you should have this kind of form. It should be alpha plus beta 1 times x plus beta 2 plus times x and so on. That's a linear form, right? Nonlinear models would not be, it's not because you have, if you're plotting your model and you end up with a curve, it doesn't necessarily mean it's nonlinear. Nonlinear would mean that in this form, for example, you might have beta 1 times x1 divided by beta 2 times x2. And that would be a nonlinear form. So linear really only means it's only about the way you write the equation, essentially. It's an additive kind of process. And not only that, there should be, yes, a linear, it's like having, how do you say? Well, we'll talk about linearity in just a bit. So if you plot length against weight, and you were to kind of plug in a line of best fit, you would expect to have kind of a constant error along that line. So what that means is if you get all the residuals from this regression, so you get all the error, and you were to plot them, so this is how you can do it. There's specifically for linear model objects here, you can, if you just put plot fit one, you'll get 4 different plots. Here, I'm just going to look at the first one. That's the one I'm interested in to kind of test this assumption. What you want is your residual. So the residuals are on the y-axis, and for every value of x, you would want the residuals to be kind of nicely spread horizontally. You essentially don't want kind of like, how do you say? I wish I had a graph to show you this because this is actually hard to explain in words. So you can see that okay, I'm fitting a straight line through this. And I don't want my points, let's say when length is very small, I don't want all my points to be above the line and then like kind of making a curve and going below and then above again, because that would clearly mean that I didn't specify the model properly. There should be maybe some kind of quadratic term so that my line also kind of follows the points. And if I do that, then of course the residuals will be kind of nicely spread out because they will be always below, regardless of the value of x, there will be, some will be below, some will be above, and that will not change too much as x increases. So here, for example, what I can see from the residuals versus fitted is that, look at this first residual here, the one that's at 15. So I have my line, a line at 0. This is where the blue line is essentially. That first dot here you can see is slightly above that line. And we can do this for each of them. So when we increase again, we move on to the next one. This is even closer to the line. You can see that point is closer to the line, but still above. And then as we move on, some points end up being below, some above, and so on. That outlier here, where we get that extreme value, that 150 centimeter length, you can see the distance it has from the line. That's the residual. That's the distance you have from the 0 here on that plot. And actually, there is a tiny bit of a curvature here. You can't see it. And if you remember, I made up this data set. So I think with real data, you might end up with a stronger curve, because if you think about it, for every centimeter that a leopard gains, it will get quite a lot of weight actually. And the more, the bigger it is, even more weight it will gain, right? It's actually not exactly a linear relationship. Which actually you can't really see here because, yeah, this data I made up and maybe it's not really accurate. But in real life, I think you may get a bit more of a curve. And if you do get more of a curve, that means that if you try to fit a straight line through it, it will not be suitable. But anyway, that's essentially the assumption of linearity. And you can check it with this plot. If you see a very clear pattern in the residuals here with this particular plot, you can be sure that you violated that assumption. What you want is actually, I mean, what we have right now is not so bad. It's actually pretty spread out horizontally, which is actually what we want. Something I should say also, by the way, why are we checking these model assumptions? If we violate them, what's going to happen is that our estimates, so the values that we saw in the table, as well as the standard error, might be screwed. It might be unreliable. And of course, if they're unreliable, that means you can't say anything from your model. Your p-values will be wrong, everything will be wrong. So any conclusions you draw from that model, if it doesn't fit the data properly, and if it doesn't meet these assumptions, your conclusions will be wrong as well. Again, these assumptions are the bedrock. They are the foundation. If that's not valid, then nothing above, nothing that goes after will also be valid. So that's why it's about to check these assumptions. So that's for linearity. I gotta say, yeah, we don't have much time today, so I won't have time to really go in absolute details about these assumptions, but I will give you a link to a really good channel that you can check out to get more info on these assumptions and how to test for them and why they can be so problematic. Okay, what we want then, another assumption is constant residual variance. And this is something that is called homoscedasticity. So what you want to avoid is heteroscedasticity. What that means is that for any given value of x, you want your variance to be kind of like the residual error to be kind of the same. You do not want, let's say, a trumpet kind of pattern, so that if x is very small, there'll be very small error. And as it gets larger, your error is even more, because it shouldn't be the case. Like if you have a model, it will make errors, of course, because you won't predict y exactly. So there'll be these residuals around the line. But you want that error to be constant. You don't want to be more wrong for particular values of x. That would imply that maybe you forgot to add an important variable here or something like that. That again, you will see in the residual in that particular plot. If you see, let's say, a trumpet kind of pattern, then it will give you an indication that you have heteroscedasticity, and that's violating that assumption. Another one is, and this is, you want independent error terms. You don't want what you will have heard maybe before referred to as autocorrelation. So what that means is that if you make an error at one particular residual, that error should not be correlated with the next error, because that means there's clearly something driving these errors. That is autocorrelation. It can be because of, so maybe you've heard of spatial autocorrelation, of temporal autocorrelation. And of course, one way to remedy with these autocorrelation is to include that variable that is driving this pattern in the residuals. If you had autocorrelation for a particular variable, you will see that the residuals are kind of, they follow some kind of shape. So like what that means is that, yeah, for any particular residual, the previous one can be used to kind of estimate what will be the next one. That should not be the case. You want to avoid this kind of autocorrelation. So to check this, you want to plot your residuals, which did I not write it here? Okay. You can, instead of using this plot function, plot like fit1, you can plot, you can use plot, sorry, I'll just write in the chat again, of the residuals of your fit1 against a variable. Here in the chat, you'll see in the code, I just call it var. And you can do this for each of your continuous variables in your model, and you can see whether there's a problem or not. Another assumption related to the residuals. So as you can see, a lot of the assumptions are to do with the residual error from the model, which essentially gets back to, it takes you back to, how good of a fit is your model to your data. So another one is you want the residuals to be normally distributed. What that means is that you want to make, so let's say, you want less error that is very far from the line and more of them around the line, which makes sense, right? You would expect that, okay, you have an expectation of Y, and you would think that, okay, it will be more likely that it is close to the line rather than far apart. If it's not normally distributed, again, that can cause some issues. And one way to do this, is to look at this plot. It's called a QQ plot. And here we can, so yeah. Essentially, I won't go into much details again here, but what you want from this plot is you want these points to be along that line here, which is actually the case here. They seem to be quite normally distributed by error terms. And of course, you can also look at a histogram that also can help you look at normal distribution. So just do a histogram of your residuals and you'll see, yeah, the error is mostly going to be around 0, so around the line of best fit. And the further away you are from the line, less likely it is that the actual Y value will be there. Okay, so that's another assumption. There's quite a few assumptions that I'm not even mentioning here, but I'm really talking about the most important ones. You don't want multiculinarity. That means that if you have different predictors in your model, so you have this response variable, of course, but among your predictors, you don't want two of them to be correlated, because if they are, they will take on the variance of the other. Your estimates for each of them will be wrong, simply because they are correlated. So that's called multiculinarity. LM can actually withstand quite a lot of multiculinarity before it actually becomes a problem. So don't worry about it if you do have some degree of correlation. One way to check it is with simply a pairs plot. So you can type pairs and your data set and the variables in your data set that are continuous, because you want to look at collinearity between continuous variables. And you can see how, whether they are correlated or not. You can get the same plot with not pairs, but plot. It's the same. It will do exactly the same thing. A function that I really like is called ggpairs in the ggalli package. So this is something we haven't done yet, is to load an extra package to help us with get extra functions. So this is called ggalli. This is how you load it. So you have to install it first with install packages and the name of the package in quotation marks. I will import it from the CRAN repository automatically. And then you'll have access to a bunch of functions that package has. You have to load it beforehand though, so using library. And the function that I'm interested in is called ggpairs. You see it's very similar to the notation we had above. We're just calling the variables that we're interested in comparing. And I like this one. It's very similar to the previous one, as you can see. But it also gives you the correlation coefficients, and the stars there indicate whether this is a significant correlation or not. You can see the strength of that correlation. This is the same Pearson correlation coefficient that we had already seen. Plus, it will tell you also the distribution for each variable. So here you can see, yeah, your variables so it's a density function. It tells you that, yeah, your variable is they all seem to be quite normally distributed, and they all seem to be quite correlated as well. But not all of them are as correlated to one another. For example, that correlation coefficient of 0.6 BCI1 and length is not as strong as, let's say, weight versus length, or let's say BCI2 and BCI1. BCI2 and BCI1, we use two very similar methods to calculate BCI. So we should not add both to the model if we want to use BCI as a predictor, because they are so strongly correlated, they will take on the variance of one another. So your estimates will be completely screwed. skewed for these two. But actually BCI1, let's say, and length, if you want to have length as a predictor and BCI, well, I guess, yeah, the correlation is not, it's significant. So I would avoid including both, but it's not so significant that it may cause problems. So again, there's some wiggle room there.
And also, like, this is just for example, because technically weight and length were used in the calculation of BCI. So it's just problematic if you look to try to then look at if weight and BCI are correlated. I mean, there's an autocorrelation there between your response and your predictor.
Right. Yeah, okay. Another assumption is that you didn't omit important variables in your model. So of course that's difficult to assess because you have to use your intuition about your system and whether you did omit. So let's say you're trying to fit a model with very unimportant variables, then you might not get really good results. So hopefully you have included all the variables you think are important to test your hypothesis. Yeah, I guess whenever you see kind of patterns of autocorrelation and so on, it gives you a clue that you may have omitted something very important there. And other than that, yeah, you kind of, sometimes it's also with modeling, it's a lot of trial and error. You have to come up with a model and test a set of predictors. Maybe you want to transform your predictors a little bit to fit the model assumptions, which can help you, for example, not having, let's say, like to meet the linearity assumption, for example. And you'll build a second model and you'll see that one will fit the data better than another. Okay. So yeah, I advise, so again, we don't have much time to go over all of this. This is, you could make an entire, you could make an entire workshop on just linear models. So I just want you to have a kind of an introduction on what it is and what it's used for. I really recommend that channel, zstatistics.com. I use it myself quite a lot, and it actually inspired quite a bit of what we did during that course. So check it out. There's all kinds of videos about descriptive statistics, a lot of what we covered actually. And there is a really nice section on regression with also, there's, I think, an hour-long video on model assumptions and how to detect them and how to deal with them and why they're causing problems. Again, it's important to mention them here, but yeah, we don't have time to go on to spend so much time on individual assumptions. Z statistics. No, that is, yeah, Z statistics. Yeah. Okay, and this is on the side. I'll send you the slides there. You can get the link here. All right. Yeah, sorry, I thought we would have time for a practical, like an applied example. That's why I sent you that ticks dataset. So I wanted to have ticks as a response variable and kind of be able to predict the number of ticks based on maybe the body condition and the different sex and locations. Unfortunately, we won't have time to do that. Yeah, feel free to try it on your own time. And if you have questions on what the results you get, we'll be happy to answer them. So don't try to do this. I'll send you the data so you can try it yourself and try to build a linear model with multiple predictors and see if you violated any of the assumptions, which you should be, because tick number is a count, it's count data, and technically you should not have the Gaussian kind of linear model will work actually if there is kind of a continuous response, like how do you say, normally distributed data, like the Y variable at least. With count data, you might get some problems and you'll see that you'll violate some assumptions. So you might have to transform the number of ticks. For example, you can log the number of ticks and then you should get model results that are valid, because you won't be validating the assumptions. So just try it on your own time. And if you have questions, I'd be happy to see the results you get. So you can send a message to the group. And yeah. Anyway, so for the remainder of the session, I wanted to go a little bit more about, okay, so we do stats, and of course, stats can give us insights. It can inform us about a larger population, we can test hypotheses. And then with these results, especially when it comes to conservation, we're going to want to make decisions. We're going to inform our decisions, hopefully based on these statistics, right? And this has been done for a long time already by people. So I want to go through an example with you to make you so that we can understand where things can go wrong, let's say. So going further, what do we do? So consider this example. During World War II, the Allied forces, they wanted to make their planes reinforced by like putting some like I don't know, like reinforced materials on some parts of the plane. Of course, you cannot do that on the entire plane because then the plane will be too heavy, right? So you want to focus on the areas that need it the most. So you collect data. That is the sampling design. For every plane that returned from their mission, people counted the number of bullet holes that was on the plane, noting down the location of the holes. Okay, cool. So we have data, and we're going to do a test. So for this kind of test, I'm not going to go into details, but you might want to do, for example, a chi-square test, for example, to check, are all the bullets kind of spread evenly on the plane, or are some areas affected more than others? Okay. So this is kind of like the null hypothesis. By default, we'll assume that the null hypothesis would be there's no difference, which would mean in our case, all the areas are hit just the same. Alternatively, some areas could be hit more often, right? Based on our data set. So we rerun our test, and if we do that, hypothetically, we'll get the result that no, there is not. You can see from the diagram, some areas do seem to have clusters of bullet holes rather than others. And we then reject the null hypothesis. So what decision do we take? And I want to hear what you think. So what should we do? Where should we reinforce the plane based on these results? Any ideas? Like, what would you do if you had these results and you were the general, let's say, and you had to take a decision? What would you decide? And of course, it's a trick question, but let's see what you come up with. So Riaz is saying the wings, okay, or the tail. All right. And of course, it seems to make sense, right? It's like, well, it has more bullets. It seems there's a lot of bullets on the wings and on the tail, so makes sense to protect them, right? Because that's the areas that seem to have the most hits, right? But actually, it's mathematicians from Hungary called Abraham Wild. He actually is at the origin of a test that is used very often, even now, called the Wild test. For actually when we compare models and we look at the goodness of fit of the model. Wait, so he's that mathematician, he was working on this problem, and he said, actually, no, there's a very important bias here in your sampling. You are only looking at planes that return from their mission. You're not looking at any of the planes that did not make it back. So actually, where you get bullets is actually not necessarily an indicator of where you should protect your plane, but these are the areas where the plane gets hit and the plane actually doesn't go down, so it is actually able to return to base. So the actual decision you should take instead, because you have this bias, it's called the survivor bias, because you're only actually looking at very specific planes, not all of the planes. You're missing all the ones that are missing, essentially. So the decision instead should be the opposite, is that you should reinforce all the areas that do not have bullet holes, because these are actually the most sensitive. The cockpit, the engine, and and of course, if you're a military person and you know your planes really well, it would make sense, right? And you might be aware of this bias. So this is just one example of how, of course, stats give us answers, but ultimately we need to know our systems really well so that we don't misinterpret our results, so that we don't end up taking the wrong decisions based on the stats results that there is. the stats will only be as good as your sampling design, making sure you have no bias. So if you want to really test the questions you are testing, you need to use the correct test, you need to make the right inference, and of course, sampling in a way that is meaningful for your question. In this particular case, the sampling was biased. So of course, you're running stats and they will give you certain answers, but if you have no idea about your system, and if you, of course, sampled in a way that is biased, then you might end up having the wrong decision. So I was hoping to kind of go through this sticks example with you to see what it means. So yeah, and something I should say again, well, which I should say as well, is correlation is not causation. If you see two variables being correlated, even if your response variable is a particular response variable, be very careful into your conclusion about whether the X variables you chose are causing this Y variable. They might be correlated, but they might not be caused. So if you look at leopards, for example, you might find maybe more ticks in males or females, I don't know. That, of course, could be due to many processes. So you have to be very careful about your conservation decisions, your management policies based on your results, because if two variables you find are correlated, the stats will tell you they are, but you have to be very careful about your conclusion about the cause, the underlying mechanism at play there. And unfortunately, with a lot of the stats that we covered in this course, we are not looking at causation as much. And there are other statistical methods that can test causality in a better way. So for now, with the tools that we have, at best, we can get results and know whether variables are associated, whether one is associated with another. But when it comes to really making conclusions on their causality, we have to be careful, and that's when knowing about your system will give you a lot of information. And yeah. And I guess we'll stop here, right? Any questions? I'll have to go, actually. That's why
Okay, you go. I'll take the questions.
Okay, fine. Anyway, thank you, everybody. It was a great workshop. I really enjoyed it. I hope you did too, and that you learned a lot. And
thanks, Guillaume.
Yeah. So now, if you have questions about everything that we covered today, and we'll answer.
Yeah.
All right. Bye.
Bye.
All right. So yeah, we can talk about, I hope everyone understood LMs. I feel like we did go kind of fast over that whole section, and I'm here to help with any doubts that you might have. Okay, I'm just saying, and you can just unmute yourself and talk about and ask if you want.
I wanted to ask one thing regarding the normality of residuals.
Right.
If my variable is normally distributed, can I assume that my residuals are also normally distributed?
Not necessarily, which is why, usually that is the case. It's unlikely that if your variables are normally your variable is normally distributed, the residuals won't. But it depends on how well your independent variable or your predictor is predicting it. Like the modeler might predict some things so that even if the variable is independent, the residuals are not.
Okay, and is the vice versa case true? Like if my residuals are normally distributed, can I assume that my variable?
No, not necessarily.
Okay.
No. Residuals is just about how much deviation from your prediction there is, your real data.
Okay.
So let's say, like the example that Guillaume gave, where you had, 1 second, I'll just take out the, yeah. So for example, in the example that Guillaume gave here, that is your line of prediction. Now, the residuals is just about what these deviations from the line are. So if you have a lot of deviations towards this end, not so many here, and that is your residuals. So the residuals are not necessarily correlated to how your data is distributed. The residuals are a function of how well your model, so basically when you're running a linear LM, it's a linear model. You're telling it, I am assuming that these are the factors which affect the distribution of this variable. So the residuals are sort of a gauge of how well your model is predicting the data.
Okay, so it doesn't matter whether my dependent variable is normal, but it matters whether my residuals are normally.
Yes.
Okay,
Yes.
thank you.
Okay. All right, so I guess if that's it, you guys can always just email on the group if you have doubts. We can clear it there, and I will send you links for our help, and then we'll also send you the link to the Z statistics video. And I guess that's it for today then.